Hi, I'm Fabio and welcome to the third course of our Machine Learning Mathematical Foundation course series. In this course we will talk about matrix decomposition. To do so, we will retrieve the concept we studied in the previous courses about linear algebra and analytic geometry. Matrix decomposition, in fact, leverages those concepts to simplify the information that matrices carry on, in order to also to approximate those matrices. So in the rest of the videos we will see that the simplicity leads to a better understanding of the matrix meaning and about its properties. But first, let's recap what we studied in the first course when we talk about linear algebra. Well, we studied and defined a vector space, a space where we introduced some obvious operation and properties between its elements, the vectors. We have then defined the matrices, which represent vectors in a particular vector space, and allow us to represent those vectors in a compact way that facilitates the computation of multiple simple operations in one shot. We have then defined the basis, which is how we view a vector space, our set of coordinates. And we've seen that through linear mappings, we are able to change our point of view, our coordinate system. In the second course, when we talked about analytic geometry, we have defined the inner product, which is a general operation that induces norms, which are useful to define the length of the vectors, metrics, in order to measure the distance between two vectors. Through inner product, we also seen how to characterize orthogonal projections, and thanks to these transformation matrices, the projection matrices, the orthogonal projections allow to project vectors on a vector subspace in a way that the original and the projected vectors at the minimum distance. We've seen another type of special linear mapping, which are the rotations. And we've seen that their transformation matrix is characterized by sine and cosine elements. So in the third course, when we will talk about matrix decomposition, we will see and define the matrix determinant, the eigenvalues and eigenvectors, the Cholesky decomposition and Eigendecomposition, and a singular value decomposition. But first thing first, let's talk about the matrix determinant. We will see that the determinant will enable us to measure the volume in a vector space. But let's first recap in a little bit what we have defined about the matrices. Well, a matrix is a tuple of elements ordered according to a rectangular schema. So a matrix is characterized by columns and rows, and for example, in this slide we can see a matrix with m times n elements. Also, we have seen that with this definition, matrix can be a representation for elements in a vector space. We've defined a particular type of matrix, which is the identity matrix, that has 1 on the diagonal terms and 0 elsewhere. The identity matrix is a square matrix. We have defined the trace of a matrix, which is the sum of the diagonal terms. We have defined also the inverse matrix, which can be computed only for squared matrix. And the original matrix multiplied by the inverse matrix return to us the identity matrix. We've then defined the transpose matrix, which is the matrix flipped onto its diagonal axis or diagonal elements, as we can see in this picture. The transpose matrix can be used to take a generic matrix, a rectangular matrix, and transform it in a squared matrix by multiplying the original matrix between the transpose matrix. We have defined also, in talking about analytic geometry, other two properties. A matrix is said to be symmetric if the original matrix is equal to its transpose. We have then defined that a matrix is positive definite if the inner product between x and x is equal to 0, is greater than 0. So let's talk about now about a determinant. And in fact, we want to be able to evaluate the volume determined by a set of vectors. Looking at this image, for example. But first, we want to determine what we mean by a set of vectors, volume by a set of vectors, and then we can define a metric to measure it. Well, this space represented in this picture is said to be a parallelepiped and is defined in this way. We take the vectors that define this parallelepiped and we take a linear composition of these vectors, the n vectors, with coefficients between 0 and 1. As you can see, all the vectors given by the linear combination of n vectors with coefficients 0 and 1. For example, on a plane, we can say that P is a parallelogram. For example, here we have a parallelogram which is a square because we've taken the standard basis. With a generic two vectors, here is our parallelogram. In 3D, on 3D space, we have a parallelepiped. Again, taking the standard basis, the canonical basis, we can see that P is a cube. Also notice that P on a Rn space has no volume if it is flat, of course, which means that at least one of the vectors that define P lie on a subspace in Rm. So M should be less than n because it's a subspace. And this condition is satisfied happens only if the n vectors are linearly dependent. So at least one of those n vectors can be written with a linear combination of the others. To have a chance to define the parallelepiped with a positive volume, so we need at least to get a set of n vectors, of course. We have seen that if we take less than n vectors, we are in a subspace that has a volume equal to 0. Every of these n vectors have n components. Of course, if we take n vectors, the volume greater than 0 is not guaranteed, because the volume can still be 0 if the vectors are linearly dependent, or one of them has 0 length, so is the null element of the vector space. So we can write P using a matrix. In fact, consider that we need to define n vectors, and each of the vector has n components. So A here is a square matrix. Now let's define a linear map that computes the volume. Here we define this function takes a square matrix and returns a real value. We take a real value and not a positive one because we want to have a result assigned volume. We will see why in a few minutes. This function is said to be the matrix determinant, and is also indicated with that of A or this notation. Notice that since the determinant is the sign volume, if we take the absolute value of the matrix determinant, we get the actual volume of our parallelepiped. But we can't choose any function we want. We need to define some properties, some conditions. Here the determinant has to follow 4 conditions. The first one is the unit volume condition. Of course, if we want to measure something, we need to define a unit measure, as it is the same for the meter, the liter, and so on. We need to define a unit volume. So the parallelepiped composed using the canonical vectors, the standard basis, form the unit cube, and we say that its volume is equal to 1. The parallelepiped generated by the canonical basis is the identity matrix. So here we can say that the determinant of the identity matrix should be equal to 1. The second condition that this function, the matrix determinant, should follow is the scaled volume condition. If we scale a column of A by a factor lambda, then the determinant is multiplied by lambda. We are basically scaling the volume, the dimension of A, which is our parallelepiped. Here we can represent this operation by taking the generic scaled vector, and we see that we impose that this is equal, the determinant of this matrix is equal to lambda of the determinant of the original matrix. Again, since the absolute value of the determinant is equal to the volume, we can say that lambda times the determinant, and then we take the absolute value of this computation, is equal to the absolute value of lambda times the volume of A. So the volume can't scale with a negative number here, but the determinant can do so, since it's a sign volume. The third condition that should lie on the determinant function is the vector swapping condition. If we swap 2 columns of A, the determinant is multiplied by -1. Here, for example, we swap the first 2 columns, and we get this is the matrix where the 2 vectors are flipped, is equal to the determinant of the original matrix times -1. Again, since the absolute value of the determinant is the volume of our parallelepiped, here the sign of the permutation does nothing and the volume is preserved. The fourth condition that should lie on the determinant function is the vector replacement condition. So if we replace a column with a linear combination between the column we are replacing and the other columns, the determinant doesn't change. Here we can express, for example, a generic matrix where the we substitute the first vector here with the vector w, and w is a linear combination of the vectors, the first vector and the one of the others. The determinant doesn't change here. In this picture we can see why, but let's move on. So, the determinant is a function that takes a squared matrix, returns to us a real number, and follows four conditions. The determinant of the identity matrix is equal to 1. Scaling a row or a column, before I talked about a column, but we can say the same for rows. Scaling a row or a column of A by a scalar lambda multiplies the determinant by lambda. And swapping two rows of two columns of A multiplies the determinant by -1. Finally, replacing a row or a column with a linear combination between the row of column itself and some other columns or rows leaves the determinant unchanged. Thanks to this condition, the determinant is uniquely defined. We will not prove this, but we can see that the determinant is uniquely defined. Since the determinant is uniquely defined, thanks to these conditions, we are able to compute it now. In particular, there are several ways the determinant can be expressed. Here, I want to explain to you the Laplace expansions. So we just have to choose, we can do the same for columns, but for simplicity we will consider here and in the further slide only rows. So we choose one generic row, and the determinant of the matrix can be computed between the sum between the columns of V, the element in the position ij, and this term Cij. Cij is said to be the cofactor matrix, and in fact is a sigmed determinant of this matrix. This matrix is the A matrix without the ith row and the jth column, such as the resulting matrix has size n-1 times n-1. This expression could seem very abstract, but let's first see that now this Cij can be expressed as a signed determinant. So the determinant of A is a weighted sum of the determinants of the n submatrices of A. Of course, each of these submatrices of A has a size n-1 times n-1. In order to characterize this Laplace expansion, let's take a look for an A matrix with dimension 1 times 1. Of course, the determinant is equal to A. The formula is pretty straightforward. But let's take a look to A with the dimension 2 times 2. So we have 4 elements. Now, what we thanks to Laplace expansion, we, for example, take the first, here we choose E equals to 1. So we move through the first row. We take the A element, and then we have to compute the determinant of this submatrix that is determined by excluding the ith row and the jth column. Here the ith row is 1, the first, and the column is the same, is the first column. So we have to compute the determinant of D. Here we have A times the determinant of D. Then we have the sigmed. Here we will have the sign, but we have B times what? the determinant of C. Remember that the cofactor matrix is signed, so here we have a minus. Again, thanks to what we've seen for a matrix with dimension 1 times 1, the determinant of D is equal to D and the determinant of C is equal to C. So we get this expression for the determinant of a 2 by 2 matrix. We can do more, and we can, for example, compute the determinant of a 3 by 3 matrix. The algorithm is the same. We take here the first row, so take the A element and we multiply by the determinant of the submatrix, which is this one. Then we have to do the same for B. We take B and we exclude the first row and the second column. So remains the determinant of the D, F, G, E. Here we have. And we can move on. Now, the determinant of a 2 by 2 matrix, we can compute these determinants thanks to the previous slide. But we already understood how we define the determinant and how to compute it. So, in order to measure the volume of a parallelepiped. So, why we defined a single volume function to measure it? Well, because this function also extrapolates the orientation of the plane. But in order to see these properties, we need to understand that the matrix from which we are computing the determinant could be interpreted as the transformation matrix of some linear mapping. For example, here, let's take this linear mapping, this endomorphism that goes for Rn to Rn. Here we have our transformation matrix with respect to a basis in V, which is, of course, Rn. So, what does this linear mapping, this endomorphism? Takes a volume defined by the canonical basis and changes the vectors and the volume underlying those two vectors that define our parallelepiped, our parallelogram, sorry. In fact, here C is a unit square, and by the first condition of the matrix determinant function, the volume of C is equal to 1. Then the volume of P here is the absolute value of the determinant of what? Of the transformation matrix. But why we have not defined just the volume function? Well, because the linear mapping scales the volume of any region in Rn by this factor, but it also changes the orientations. Here we can see that the factor is always the same even if we scale up the vectors. Nothing important to our task. But let's take a look to this transformation and what it does to these two vectors. As you can see, x1 is below x2 and f of x1 is above now. The determinant, if you compute the determinant of this function, we can see that it's equal to -1. So this sign of the determinant describes the change of space orientations. Because the determinant is equal to -1, so the volume is always the same, is equal to 1. So f preserves the area but reverses the orientation of the plane. You can see this by looking at these two arrows. This property is can be seen in a more direct way, taking a look to this picture. We've seen this circular arrow, which is the anti-clockwise arrow, and is our original picture. If we do a linear transformation with determinant equal to 1, for example, a rotation, the arrow is still anti-clockwise. Here we scale, okay, but that's the interesting part, the reflection. Determinant is equal to -1, and now the arrow is clockwise, moves clockwise. So we can say that a mirror is a linear mapping with determinant -1. If we move away a little bit from the determinant, of course, if we move a little bit away from the mirror, the determinant will be negative, but the linear mapping could scale our face, for example, by a certain factor. Matrix determinant has some relevant properties. For example, the determinant of the transpose of a matrix is equal to the determinant of the matrix itself. The determinant of a multiplication between matrices is equal to the multiplication between the determinants. Also, if A is invertible, then 1 is equal, of course, to the determinant of the identity matrix, the first condition we defined for the determinant. But if A is invertible, the identity matrix can be written as the inverse matrix times the matrix itself. Thanks to the second property here, we can say that the determinant of this multiplication is the multiplication of the determinant. And since this product must be equal to 1, then the determinant of A must be unequal to 0. Fourth property is that if this matrix is defined, the inverse of a matrix is defined, then its determinant is equal to the determinant of A to the power of -1. There are special types of matrices in which the determinant computation is very, very easy. And here we can see the three cases: the upper triangular matrix, the lower triangular matrix, and the diagonal. In those three cases, the determinant of the matrix is the product of its diagonal entries. This can be seen by applying the Laplace expansion. Of course, between these three metrics, the diagonal one is the simplest one, because elsewhere from the diagonal is equal to 0. So in the first section, we have defined this new function, the determinant, which will allow us to compute the volume of a parallelepiped. Now we will see and we will use the determinant to define other concepts like eigenvalues and eigenvectors that are the pivots of a linear transformation.